All right, 8:30. Good morning, everyone. Happy Friday. Today what we're going to do is, let me give you a rundown of where we're going. This is our last lecture before exam 2. Luckily, we have today and Monday to go through it. I'm sure we're going to get more than halfway on this lecture. So on Monday, we'll finish it up and have some games as a review. I will bring prizes. So please be here on Monday. I'm going to postpone the essential cardiovascular calculations until Monday as well, but today we're actually going to be working on it in class to finish it up. Again, don't forget that our exam has been postponed until Wednesday, okay? All right, I am recording this lecture. It is recording now. Today what we're going to be concentrating on are first the physics of blood flow, which will really help you with the rest of your questions on the cardiovascular essential calculation sheet. Then we're going to go through each of the blood vessels. We'll talk about arteries, arterioles, capillaries, venules, and veins. And then we'll work on the flow in the vertebrate circulatory system and regulation of circulatory systems by the autonomic nervous system and baroreceptors. That's how we'll end up. Then that's going to give us an opportunity to really put a lot of things together. We'll revisit Ohm's law, and we'll talk about the sympathetic and parasympathetic system. So with that, I do have a few top hat questions. First of all, I did reserve this room between 1:30 and 3:30 today for a review session, but I have had a lot of students that can't make it tonight. So the first top hat question today, if you want to get your top hat questions out, or your devices out, would you rather have the review session today, or do you actually want to have the weekend and I'll reserve a room on Monday afternoon?
Would it be at the same time?
No, I think on Monday it would be later, between 4 and 6. I don't think it'll be in this room. I'd have to reserve a different room, possibly B45 or. So the location of the room will be here on St. Paul campus, but it's undetermined at this time. If you'd rather have it today, this room is already reserved between 1:30 and 3:30. All right, so again, I'm shooting for Monday 4 to 6. All right, we have 82 people that have already answered. All right, I'm going to just see what the majority is saying here. I'm going to close it. And here's what you're saying. Monday. All right. So what I'm going to do, since a lot of people can't make it this afternoon, I will find a room and reserve it between 4 and 6 on Monday afternoon. Does that sound all right with everyone? Okay. So today, there is no review session, just so you don't know. Don't show up at 1:30 today. Okay, let's go to the next question. I have 3 top hat questions today, and this is a review of what we've talked about with the cardiac cycle. The cardiac cycle last time. So, think about the anatomy of the heart and the blood flow. Okay, so a pulmonary embolism is a fairly common post-operative complication in hip replacement surgery. Clots formed in the veins of the legs break loose and end up lodging in the lung. They end up in the lung because A, the clot travels to the heart where it is pumped to the lung by the right ventricle. B, the clot travels to the heart where it's pumped to the lung by the left ventricle. The clot bypasses the heart and is pumped directly to the lung from the hip. D, the clot is attracted by the high oxygen of the lung. E, all of the above. So, knowing what you know about the heart and blood flow, Which answer is the best? And you can talk to your neighbors, yes. All right, we're up to 75. I'll give you about 10 more seconds. All right, so I'm going to go ahead and close this one. See some last minute answers here. All right, and the correct response is A. Yes, good job. A is the correct answer. 92% of you all got that right, so that's fantastic. Remember, when the right ventricle contracts, it propels the blood through the pulmonary artery, still deoxygenated blood, goes through the lungs, comes back through the pulmonary veins into the left atrium. All right, so the next one here is a little tougher. The amount of oxygen is greatest in the blood found in the A, right atrium, B, right ventricle, C, venules, we just mentioned that term earlier, D, left atrium, E, superior vena cava. So think about oxygenated and deoxygenated blood. Think about the blood flow through the circulatory system. So where is the amount of oxygen the greatest? Just to help you out here, venules are the tubes that connect the capillaries with veins. So we've got about almost 80 students that have answered so far. I'm going to go ahead and give you 10 more seconds. Okay. So I'm going to go ahead and close this one. And the correct response is D. Yes, good job. The left atrium. So once the blood has it's flowing through the lungs, it comes back through the pulmonary vein. It's one of the only veins that has oxygenated blood and enters directly into the left atrium. So yes, the correct answer for this question is D, left atrium. Nice job. Most of you got that right. Perfect. This is the last one for today. All right, so this is a tough one. We talked about the cardiac cycle last time and the Wiggers diagram. During the isovolumetric contraction, all right, remember iso means same. Volumetric is referring again to the volume. During the isovolumetric contraction phase of the cardiac cycle, you're in systole. It's the beginning of systole, ventricular systole. The AV valves are A, closed or B, open. And the aortic pulmonary semilunar valves are A, closed, or B, open. So the first one is they're both closed. The second one is the AV valves are closed, but the semilunar valves are open. C is the AV valves are open, but the semilunar valves are closed. D, they're both open. So I did have a really good question after class. I just want to make sure that students are putting this all together. Remember, the left and right AV valves are the tricuspid and bicuspid. The tricuspid is the right AV valve. They're synonymous, those terms. And the bicuspid or mitral valve is the left AV valve. So during the isovolumetric contraction, the isovolumetric contraction phase of the cardiac cycle, what's going on with the valves? All right, when we get to 75, I'll give, yep, there we go. Give you 10 more seconds. All right, did everybody get a chance to answer this question? All right, we're up to 90 now. All right, so I'm going to go ahead and close this one. And the correct response is A. Right, okay. This is a little bit tougher. This is before the ejection phase in systole. Before the ejection phase. So in the beginning of systole, this is when the contraction of the ventricular muscle starts. When that contraction of the muscle starts, first pressure inside those chambers are increasing, and but no blood is being ejected yet. This is technically an isometric contraction, right? No blood is being ejected. You know that because this is the same blood volume, okay? So pressure is building, building. All the valves are closed. It's not until the pressure in the ventricle exceeds the pressure in the aorta, that's when the semilunar valves open up and blood is ejected. So during the first part of systole, this is known as the isovolumetric contraction, and no blood is being ejected, all valves are shut. So it's good to kind of review that cardiac cycle one more time. Again, we will review this on Monday during the review session for sure. So that's all the top hat questions I have for today. Let's get started on our last lecture, and we're going to jump right into the cardiovascular essential calculation sheet. I'm going to give you some time to work on it. So first, let's talk about the physics of blood flow. This looks very daunting, but you already have all of the tools to really understand this. This is actually at the top here, the law of bulk flow, which is Ohm's law. This is just Ohm's law. It's just rearranged a little bit. So remember, blood is always going to flow from high pressure to low pressure. This is the driving force, the pressure gradient. We've rearranged it. Remember, the pressure gradient or driving force equals flow times resistance. Q in this case, a lot of times bulk flow is symbolized by Q, but this is just the flow or cardiac output in mils per minute. So this is just another variable that can be representative of flow. So the law of bulk flow, this is just cardiac output. So in this case, cardiac output is equal to mean arterial pressure because there's no pressure in the veins. We can take that out of our pressure gradient. Divided by resistance, okay? Flow equals pressure gradient, and that's the mean arterial pressure minus the venous pressure. Venous pressure is 0, so we can just say mean arterial pressure divided by resistance. And in that chart, we talked a little bit about what factors, what variables play a role in resistance. And we said things like the radius of the tube, the length of the tube, viscosity. So this is breaking down resistance and defining it. Resistance is equal to 8 times the length of the tube times times viscosity. You can see here's the terms down here, viscosity, divided by over pi r is radius of the tube to the 4th power. Okay? This is like Fick's law of diffusion. We're not going to run any numbers, but I do want you to know the relationships, right? And how that would affect resistance. All right? So if we plug these terms of resistance, remember that is on the bottom in the denominator, we would have to flip these variables, right? So we're going to just substitute R for these variables, and here's how it would actually be written out. Flow is equal to the change in pressure, the pressure gradient. We flipped the resistance terms because resistance is on the bottom. Pi r to the 4th over 8L viscosity. All we did was plug that into the equation, Ohm's law. Okay, so what this says is, I want you to revisit this, the radius to the 4th power. That is really powerful intuition. What's this is saying is small changes in the radius of the tube translates to huge changes in resistance. So I'll say that one more time. Small changes in the radius of the tube. And think about those smooth muscle cells that constrict around the vasculature. Right? When they contract, they restrict, they decrease the radius of those tubes. So small changes in the radius of those tubes translates to huge changes in resistance. Okay, so that's known as vasoconstriction and vasodilation. When you think about those smooth muscle cells that surround these tubes of the vasculature, when you constrict, you can use the term vasoconstriction and vasodilation now, when they relax. Okay? The other thing I just wanted to mention is viscosity. Viscosity is giving you some idea of the thickness of the blood. This is why doping is illegal. Doping. So when athletes, you probably heard this, with elite athletes, sometimes they will, if this is illegal, by the way, they would actually take a large portion of their blood volume out, and then right before a race, maybe a day later or so, they will inject it back into their blood. They allow for their body to actually increase the red blood cells, and then they inject more red blood cells, right? You can imagine the viscosity is going to go up tremendously, and it's going to put a lot of pressure on the heart. It's actually really dangerous, okay? So that's speaking directly to viscosity and how it relates to an increase in resistance, okay? So, problems with, and again, this is just physics of blood flow. So again, what we're going to be doing is we're going to be concentrating, you've seen this slide before, we're going to be concentrating on the vasculature, going through the different tubes, and I'll give you some characteristics of the arteries, arterioles. As we go through the vasculature, the arteries branch into arterioles. They continue to branch into capillaries. And then the branching, it actually comes back together into fewer venules than the number of capillaries. And then they merge into veins, and then finally the inferior and superior vena cava. So there's extensive branching in the capillaries. All right, looking at the blood pressure too, remember the systolic and diastolic pressure, right? This is what's happening in the arteries. What we'll learn too is there is a large resistance in the arterioles that really drops the pressure. Again, the pressure continues to drop until we get to the veins, and eventually it's basically zero right before you get to the vena cava. So, continuing with the physics of blood flow, I'd like you right now to actually get out your essential calculations, your cardiovascular calculations. This is going to help you with some of these variables. Now that you know what Q is, let's go ahead and actually, I have to draw on an envelope here. All right. So the first equation that I want to, it's a pretty simple one, but I want to break down flow for you. There's a concept here where it's called the law of the conservation of mass. So when you think about cardiac output, you can think about the flow through the entire vasculature being the exact same. All right, so when you look at flow, you have to think about the flow through the entire vasculature. And flow is always constant. It's the law of the conservation of mass. So taking a look at, I think it's the last two problems on the front sheet. Let's just see what that says. What is the total blood flow through the pulmonary capillaries? And the other one is, what is the total blood flow through all of the systemic arteries? This is a little bit of a trick question. All right, so if you've already calculated cardiac output as what? What did you, we already talked about this, but remind me, what is cardiac output?
5,000.
That's right, 5,250. That value is the exact same for 4 and 5. I'm sorry, 5 and 6. 5 and 6. So the answer to 5 is 5,250. The answer to 6 is 5,250. Okay? So this is known as the law of the conservation of mass. All right, so if Q is the same through the entire circulatory system, let's try to figure out the velocity of blood. And I'm going to give you some intuition about the velocity of blood. And this is going to be to your last question there. So the equation that I want you to think about is this one. I lost my Sharpie, so I apologize. So I'm going to try to zoom in on this one with the document camera. Oops. All right, so it is Q. I need a better pen. Q is equal to velocity times area. Velocity times area. Let's try this pen. Q in mils per minute. Thank you. Thank you. Q in mils per minute, and that would be cardiac output, is equal to velocity, and this is centimeters per second or minute. Let's put minute, times area, which is centimeters squared. Area, centimeters squared. So, I'm sure you know this from chemistry, but mils is actually centimeters cubed. So, it makes sense that Q is equal to centimeters cubed over minutes. And that's equal to centimeters velocity times centimeters squared. Multiply those together, that'll give you centimeters cubed per minute. So again, Q is equal to velocity times area. So what is velocity? Velocity is going to be Q over A. And what you're going to notice is if you increase the area of these tubes, you're going to decrease the velocity. Decrease the velocity. So how does this apply to the vasculature? How does this apply to the vasculature? Going back to our slide here, what that means is, take a look at this slide down here. The cross-sectional area of the tubes, we're going from the arteries to the arterioles to the capillaries, venules, and veins. As we get to the capillaries, the cross-sectional area goes up tremendously, right? The area goes up tremendously in the capillaries, and then as those branches, those tubes merge, the cross-sectional area goes down. So you have to look at the vasculature in its totality, right? All of the capillaries and the area of all of those tubes. And because of that, as the area increases, the speed of blood, that velocity, decreases tremendously. That actually makes sense because you want the blood, the speed, to slow down in the capillaries to allow enough time for oxygen exchange and nutrient exchange. Okay? So the velocity of blood really slows down in the capillaries, allowing enough time for oxygen and nutrients to be exchanged. Now, this is somewhat counterintuitive. A lot of students think about the capillaries like a car traffic jam, right? They think about the blood flow like all the cars trying to merge into one tiny little capillary, right? And then once they get into the capillary, they think, right, the intuition is the blood flow starts, that speed increases once you get into a single file. That's not the way I want you to think about it, okay? We're thinking about the capillaries, all of the capillaries together, okay? And blood's going to flow through the least resistance, so it's actually going to flow into all of those different capillaries, and the velocity actually slows down tremendously. So the analogy that I want you to think about is, think about the Mississippi River, right? The Mississippi River. The river, when it's the largest, right, it is going fast. If you fell in the Mississippi River when it is, really huge and, a mile from one bank to the other, you would be swept away, right? The velocity is really high. But as it branches into, different river, then streams, right? And as it, like when you get down into the Mississippi Delta, and you can walk across it, you'll notice that the velocity is really slow, right? So when it starts to branch, you have to think about the total area of all the capillaries, and the velocity is really going to slow down in the capillaries. As that cross-sectional area gets higher, larger, you can see the velocity really plummets. So the velocity of blood is highest in the arteries and lowest in the capillaries, because in the capillaries you have that large cross-sectional area. And just to show you that equation, right, Q over A, flow over A is equal to velocity. Velocity is equal to flow over the cross-sectional area. So as the cross-sectional area goes up, the velocity is actually going to go down. So do you think you could work in a group and finish up that last question there? I'll give you a few minutes here to do that. So area is pi r squared.
And I just changed it to I don't know what it is. Thank you. It's probably confusing. Oh, okay, so I like was reading in one of mine, but this is in a different like units. So then I found videos. So I read about it. They use the left arterial pressure, right? Yeah, and we have that, or left atrial pressure. We have that. So what like I think in practice they use this and like this is the units that they use, which is equal generally to this, but if we're not using these units, we're talking about them. So I just changed it to left arterial pressure. I know, I was like, why are we doing it? But then I read more about like how to do it and okay. Because I kept finding patients without the 80 and it pissed me off because I was like, what is this 80 for? And then finally it's just a conversion factor to get it to my level. Essentially, like that's what I
All right, everyone. About 5 minutes. I'm going to go ahead and talk about the answers. So, if you haven't figured this out yet, I kind of just blurted it out here, but the velocity is equal to Q over A. And A is actually pi r squared. Area is equal to pi times radius squared. And you already know that cardiac output is 5,250 mils per minute. You divide that by pi, 3.14, times the radius squared. When you convert from millimeters to centimeters, this is what you would get, 3.14 centimeters squared. Right? And mils is centimeter cubed. So when you actually cancel out centimeters, you're going to be left with units of centimeters per minute, which is a unit of velocity. 1,672 centimeters per minute. All right, so on your exam, though, you won't have to calculate this. Again, I would want you to know that the velocity is the highest in the arteries and the lowest in the capillaries. That's the main idea here. All right, so I'm going to continue on. Go ahead and keep working on this over the weekend, and we can discuss some of the questions that you might have on Monday. We can do that during class or during the review session. All right, so a few more ideas I want to put forth. I do want to talk about, we've already talked about Ohm's law earlier. Remember, Ohm's law is the driving force times current times resistance. Driving force equals current times resistance. So when you just rearrange it, current, in this case, is going to be Q, that's flow. Remember, flow is going to stay the same through the entire circulatory system, and that's equal to the pressure gradient divided by resistance. Now, looking at resistance, you can actually model resistance in different ways. When the resistors are end over end over end, like this is what's called in series, then you have to calculate the total resistance in one way. The total resistance for resistors in series is the sum. You can actually see here, total resistance is equal to the resistance of 1 plus the resistance of 2 plus the resistance of 3. So the total resistance when the resistors are in series with each other is going to be really large. But resistance in parallel, when the tubes, we're thinking about the vasculature, and what I want you to think about is how the capillaries are organized. The capillaries are organized in parallel with each other. You can see that it is just a fraction, basically. The total resistance is equal to 1 over the resistance of this resistor, R1, plus 1 over the resistance of R2, plus 1 over the resistance of R3. Here's the take-home message of resistors in parallel. When you calculate this out, the total resistance is even lower than the lowest value of one of these resistors. So thinking about these resistors in parallel and finding the lowest resistance, the lowest value, the total resistance is going to be lower than that. So the total resistance is going to be very small. That's why the resistance in the pulmonary circulation is so low, because all of those capillaries are in parallel to each other. And I'll put this as a note on your website, but I actually found a nice little tutorial. This is, again, the physics of blood flow. Right here, it actually shows the resistors in series and in parallel. And then it actually does, here's the other one, it actually does some actual calculations. And you don't need to know all of the details here, but I just want you to realize that when you actually calculate the total resistance in series, you have to add them all together, which gives you a fairly large resistance. But if you calculate them in parallel with each other, you can see it's 1 over R1. Let's blow this up a little bit. 1 over R1, 1 over R2. You can see that the total resistance here at the bottom here, let's see, where is it? The total resistance here is less than any one of these values, right? 1 ohm is resistor 1, 6 ohms is resistor 2, and 13 ohms is resistor 3. When you look at the total resistance in parallel, it's less than the lowest value, 1. Okay? So that's why the resistance is so low in the pulmonary circulation. All right, so going back to our slides, again, I will post this so you can take a look at it. And here's where we are. This just tells you again, it's kind of giving you some idea of the resistors in series, the resistors in parallel, and again, because of the law of conservation of mass, the flow through each segment of the system must be equal. Q must be equal. So you can model circulatory systems using these electrical models, an electrical circuit. Ooh. Sorry, my phone, I forgot to tune it out. Okay, so remember blood velocity. This is a review slide. Flow is the volume of fluid per unit time. Velocity is distance in centimeters per unit time. And blood velocity is equal to Q over A. Velocity is inversely related to the cross-sectional area. So as the cross-sectional area of capillaries gets very large, velocity is slow, allowing enough time for diffusion. As we go through this, you can actually see the inverse relationship of area again in orange and velocity in green. And this actually is just a nice, this is from your textbook. It shows that these 6 molecules, they're represented as balls really, are going to move this distance in 1 minute. But as it moves into the capillaries, you can see these 6 balls in time are kind of stacked up on each other now. And it only moves a much shorter distance in 1 minute period of time. So again, showing you that we have to look at the totality of the area of all the capillaries, and you can see that that actually slows the velocity quite a bit. Remember, velocity is distance per unit time. So 6 balls in per minute mandates 6 balls out per minute. Therefore, the velocity of the balls in the smaller tubes is slower. All right, so let's take a look at some of the blood vessels. We have about 5 minutes here. I'm just going to give you some, fundamental characteristics. Arteries are going to have the highest velocity. We've already talked about that. And the pressure fluctuations in the arteries are going to be smaller than those in the left ventricle. So the left ventricle, I think you remember this slide. I'm going to go all the way back here. The left ventricle has these major fluctuations with systole and diastole. right? Systole and diastole. But when you actually measure with a blood pressure cuff, you actually put the blood pressure cuff around your biceps and triceps. And essentially what you're measuring there, you can see that the arteries actually somewhat dampen those oscillations, and you measure between about 120 and 80 millimeters of mercury. So there's a dampening effect with the arteries, right? The major artery, that one aorta, acts as a pressure reservoir and dampens the pressure fluctuations. That's actually due to the elasticity of the vessel wall. It's like pushing fluid into a balloon. A balloon has a lot of elasticity, and as soon as you force blood into it, there's going to be a recoil effect. And that's going to actually dampen those fluctuations. That recoil effect helps to keep the blood moving even during diastole. Okay, so the blood moved into the aorta and the arteries with a single heart contraction stretches those arteries. They recoil. There's going to be a recoil effect, and that continues to move the blood even during diastole. Okay, so we'll talk about blood pressure next time. A lot of students in the lab will be working on blood pressure and ECGs this next week. I just want to let you know a couple of terms that are important. Arteriosclerosis, that top term, is a general term for hardening of the arteries. A lot of times as you age, you lose some of that elasticity for various reasons, and that's known as arteriosclerosis, hardening of the arteries. Atherosclerosis is a type of arteriosclerosis. It's hardening of the arteries, but specifically due to plaque formations and high cholesterol. Atherosclerosis. Okay, atherosclerosis.
What was the cause of that one?
Plaque formation with high cholesterol. You're going to get this plaque formation within the arteries that can occlude the arteries. It can occlude the arteries, and the worst thing that could happen would be like a left coronary artery blockage, which would cause a heart attack, myocardial infarction. So I'm going to skip this. I'm going to keep going. I'll review that on Monday and talk about sphygmomanometry, which is blood pressure cuffs and how they work. But let's go to arterioles. We're moving from the arteries now into the smaller tubes called arterioles. And this actually controls blood distribution. It's interesting because arterioles have a lot of smooth muscle surrounding them. And they are a site of regulation. A site of regulation. There's dynamic vasoconstriction and vasodilation that actually occur in these tubes. They're arranged in parallel, and there are extrinsic and intrinsic mechanisms, factors, that can alter vasoconstriction and vasodilation. Sometimes extrinsic mechanisms come from the nervous system. This would be the sympathetic nervous system that can cause vasoconstriction. There's also hormones like vasopressin, hence the name. Vaso is the vasculature. Pressin is talking about vasoconstriction. These extrinsic mechanisms are coming from outside the tissue, that smooth muscle cells. Intrinsic mechanisms are monitoring carbon dioxide and oxygen, some of the metabolic states of the tissue. And these intrinsic factors can also cause vasoconstriction or vasodilation. So it's a dynamic site of regulation. Again, we'll get to some of this on Monday. Finally, the capillaries are where all of the exchange occurs. Let me just go through the type of capillaries. We'll end there. Hold on just a second. I can just go through this quickly. Continuous are held together by tight junctions, so they're not very leaky. But fenestrated capillaries, like in the kidney, they allow for small electrolytes and plasma to leak through. These are called fenestrated capillaries. And the ones that are the most leaky, they're held together by very few tight junctions, are very porous. These are found in bone marrow and in liver. Sinusoidal capillaries. All right, I pushed it to the limit again, 9:20. Have a great weekend. We're going to have the review session on Monday. I'll reserve the room and make an announcement today. Let me know if you have any questions. I can hang out here a little bit longer. Have a good weekend, everyone. Have a good weekend.
A really quick thing.
Yeah,
I
yeah.
had a slight malfunction, I guess.
Oh, yeah.
I answered all the top hat questions, and like this one says I didn't.
Oh,
answer
okay,
it,
no
so I
worries.
just want to make sure I get credit.
Absolutely, because that's the one I'm probably going to take.
Okay.
Okay, so could you actually send me an email?
Yeah,
Just
I'll
take a
send you an
picture of
email.
that, send me an
Okay,
email.
sure.
Yes.
Sorry
All
about
right.
that.
No worries. Yeah, not your fault.